In the vast expanse of space, countless mysteries remain unsolved by science. Despite rapid technological advancements and constant scientific discoveries, the universe continues to surprise and perplex even the most brilliant minds of our time. The more we learn about the cosmos, the more we realize how little we know, notes Professor Brian Greene, a theoretical physicist at Columbia University. Every new discovery brings dozens of new questions, and that's beautiful. It's how science progresses. In this article, we will explore 10 of the most intriguing cosmic mysteries that remain unsolved and present insights from leading experts in astrophysics and cosmology. 1. Dark matter, the invisible ruler of galaxies. In the early 1930s, Swiss astronomer Fritz Zwicky observed an anomaly while studying the motion of galaxies in the Coma cluster. The galaxies were moving much faster than expected based on their visible mass. This observation marked the beginning of one of modern astrophysics' greatest mysteries, dark matter. Dr. Vera Rubin, whose groundbreaking research in the 1970s provided crucial evidence for dark matter, once said, "There is nothing in nature more mysterious than dark matter. We can observe its influence everywhere, but we cannot see it directly." Modern research and hypotheses. Professor Lisa Randall from Harvard University, a leading expert on dark matter, explains, "We know dark matter exists thanks to numerous independent observations, from galaxy motion to gravitational lensing. The question is not whether it exists, but what it actually is." According to current estimates, visible matter makes up only about 5% of the universe's mass. Approximately 27% is attributed to dark matter, which we cannot see directly but can observe through its gravitational effects on visible matter. Imagine watching a couple dance in a completely dark room, where only one dancer is visible, says Dr. Catherine Fries, head of the LUX dark matter detection experiment. You can infer the presence of the second dancer by the movements of the first. That's how we detect dark matter, by its influence on visible matter. Ongoing searches. Large-scale experiments are currently underway to directly detect dark matter particles. One of the largest detectors, Xenon 1T, is located in the Gran Sasso Underground Laboratory in Italy. We use ultra-pure liquid xenon as a target, explains Dr. Elena April, coordinator of the Xenon project. If a dark matter particle collides with a xenon nucleus, we can detect a tiny flash of light and an electrical signal. So far, we haven't found any dark matter particles, but each experiment brings us closer to solving the mystery. 2. Dark energy, the mysterious force of expansion. The discovery of the universe's accelerated expansion in 1998 shocked the scientific community. Saul Perlmutter, Brian Schmidt, and Adam Rees, who received the Nobel Prize for this discovery, found that galaxies are moving away from each other faster and faster, as if pushed by some invisible force. The nature of dark energy. Dark energy is perhaps the greatest mystery in modern physics, says Nobel laureate Adam Rees. It makes up about 68% of the universe's mass energy, but we know almost nothing about its nature. It's like discovering that most of your house is made of something invisible and incomprehensible. Professor Lawrence Krauss, author of A Universe from Nothing, adds, "Quantum field theory predicts the existence of vacuum energy, but its calculated value differs from the observed dark energy by 120 orders of magnitude. This is the largest discrepancy between theory and experiment in the history of physics." Current research. Dr. Rachel Bean from the Kitt Peak Observatory discusses the new dark energy spectroscopic instrument DESI project. We're creating a 3D map of the universe by measuring distances to millions of galaxies and quasars. This will help us better understand how dark energy influences the universe's expansion over time. Professor Sean Carroll from Caltech offers an intriguing perspective. Perhaps dark energy isn't just a cosmological constant, but a dynamic field that changes over time. If so, the fate of the universe could be far more complex and interesting than we think. 3. Baryon asymmetry. Why does matter exist? Professor Andre Linda, one of the creators of cosmic inflation theory, begins the discussion of this mystery with a philosophical question. Why do we exist at all? According to the laws of physics, matter and antimatter, should have completely annihilated each other after the Big Bang. But something went wrong, and that's why we're here. Symmetry breaking. In the early universe, for every billion particle-antiparticle pairs, there was one extra particle of matter, explains Dr. Helen Quinn from SLAC National Accelerator Laboratory. This tiny asymmetry is the reason everything we see around us exists. Searching for explanations, Dr. Tsutomu Yanagita from the University of Tokyo, known for his work on baryon asymmetry generation, comments, "We're looking for processes that could have broken the symmetry between matter and antimatter in the early universe. One possible mechanism is leptogenesis, involving heavy neutrinos." Professor Sakharov, whose conditions for baryon asymmetry became foundational in this field, once noted 3 necessary conditions: baryon number violation, C and CP symmetry violation, and deviation from thermal equilibrium. The standard model of particle physics cannot explain the observed asymmetry, says Dr. Marcela Carina from CERN. CP violation in weak interactions is too small. We're searching for additional sources of CP violation in new particles and interactions. 4. Ultra-high-energy cosmic rays. Where do they come from? Imagine a tennis ball with the energy of a large truck moving at full speed, describes Professor James Cronin, a Nobel laureate and co-founder of the Pierre Auger Observatory. That's the kind of energy some cosmic rays carry. And we have no idea what could accelerate particles to such energies. The origin paradox. Dr. Angelo Alinto, a leading cosmic ray researcher, explains, according to the GZK effect, ultra-high-energy cosmic rays cannot come from distances greater than 100 megaparsecs. But within this radius, we don't see any objects capable of producing them. It's a real paradox. Modern observations. The Pierre Auger Observatory in Argentina records particle cascades created when cosmic rays collide with the atmosphere, says Dr. Karl-Heinz Kamper. We can determine the primary particle's energy in approximate direction, but the sources remain a mystery. 5. Magnetic monopoles, elusive particles. In 1931, Professor Paul Dirac mathematically showed that the existence of magnetic monopoles would explain the quantization of electric charge. The beauty of this idea lies in its simplicity, comments Professor Joseph Wilczynski. If even one magnetic monopole exists in the universe, it would be enough to explain charge quantization. Experimental searches. We've searched for monopoles in cosmic rays, accelerators, lunar samples, and ancient mica, says Dr. Arta Rajani from the MOEDL experiment at CERN. So far, no luck, but the absence of evidence isn't evidence of absence. Professor Alan Guss, author of Cosmic Inflation Theory, suggests inflationary expansion in the early universe might have diluted the concentration of monopoles so much that finding them is nearly impossible. 6. Cosmic voids, giant emptiness in the universe's structure. Voids challenge our understanding of the universe's large-scale structure, says Professor Yelena Nikolek from the Max Planck Institute for Astrophysics. Some are so large that they shouldn't have had time to form in the universe's lifetime. The cold spot mystery. Dr. Istvan Saputty, who studies the largest known cosmic void, comments, the cold spot in the cosmic microwave background might be linked to a giant void. But its size, about 1.8 billion light-years, is hard to explain within the standard cosmological model. New theories. Perhaps voids aren't just empty spaces, suggests Professor Laura Mersini-Houghton. They might be filled with dark energy or exotic matter, influencing the universe's large-scale structure. 7. The cosmological lithium problem. The discrepancy between predicted and observed lithium. 7 levels is one of modern cosmology's most intriguing mysteries, notes Professor Gary Steigman, an expert on primordial nucleosynthesis. Searching for solutions. Dr. Karen Lin from the Max Planck Institute for Astronomy explains, we carefully measure lithium content in the galaxy's oldest stars. The results consistently show a lithium deficit compared to theoretical predictions. Perhaps some lithium was destroyed by unknown processes in the early universe, suggests Professor Brian Fields. Or maybe we're missing something in our understanding of primordial nucleosynthesis. 8. The ultraviolet catastrophe of the Reionizing intergalactic hydrogen requires an enormous amount of energy, explains Professor Stephen Finkelstein. But known ultraviolet sources from that period can't provide the necessary power. Searching for ionization sources. Dr. Emma Chapman from MIT comments, "We're studying the first galaxies with the James Webb Space Telescope. Perhaps early stars were more massive and hotter than we thought. Exotic sources might also be involved," adds Professor Abraham Watt. For example, dark matter particle annihilation or mini-quasars could have contributed significantly to reionization. 9. The horizon problem. The mystery of cosmic uniformity. The uniformity of the cosmic microwave background is one of cosmology's most astonishing mysteries, says Professor Brian Greene. Different regions of space have nearly identical temperatures, even though they could never have exchanged information. Inflation theory. Cosmic inflation offers an elegant solution to the horizon problem, explains Professor Alan Gross. But the nature of the inflating field and the mechanism stopping inflation remain unknown. Dr. Eva Silverstein adds, "Some versions of inflation theory predict a multiverse. It's an exciting idea, but it's impossible to test experimentally." 10. Quantum gravity. The search for a final theory. Quantum gravity is the holy grail of modern physics, declares Professor Carlo Rovelli, one of the creators of loop quantum gravity theory. "We're trying to unify quantum mechanics and general relativity, but these theories speak different mathematical languages. String theory and alternatives. String theory is the most developed candidate for a quantum theory of gravity," says Professor Edward Wynne. "But there's no way to experimentally test its predictions yet." Professor Lee Smolin offers an alternative view. "Perhaps we need to radically rethink our understanding of space, time, and causality at the fundamental level." Conclusion. These 10 mysteries show how astonishing and enigmatic our universe remains, concludes Professor Brian Greene. Each one could lead to a revolution in physics and our understanding of the cosmos. Dr. Neil deGrasse Tyson adds, "The history of science teaches us that the greatest discoveries often come from tackling the hardest puzzles. Solving one of these mysteries might open the door to a completely new understanding of the universe." In the end, says Professor Steven Weinberg, the most amazing thing about cosmic mysteries is that we can study them and gradually approach their solutions. This demonstrates the incredible capacity of the human mind to comprehend the laws of nature.